Hi all, it's Mr. Yeager with Chemistry, and we are looking at heating and cooling curves to finish up our thermodynamic unit. Again, I'm going to remind my students that we still have reaction rates a little bit, but we are finishing up this particular Google site of thermochemistry. So this is basically just giving you a more analytical and visual of what is happening to different states of matter when you increase the temperature, and it helps us see the changes occur between those states. So that's what we're basically doing. We're going to look at graphs. So we got right here, which I guess I think I have to make a little bit smaller for everybody to see it. So there we go. Okay. We got right here essentially a heating curve. This would be called a heating curve. There is one little thing that's going on in it that I'm going to kind of ignore, and I'll mention you what that is. But this is the heating curve for water, pretty much the most common one we analyze. But essentially all substances have heating curves that look like this. It's just at what temperature are we changing the states of matter. So what you can see with this is we got on the x-axis the temperature. On the y they have energy, which I do like this. I like that it has energy. A lot of times this is just time. Okay, they usually have that measured in time. But it's more about the y-axis that we're really looking at. But with that energy on the x, that's very useful as well. We will see an increase in energy as we go along this graph as well. So what you basically look at here is you can see, obviously below zero, again, we're talking about water, we only have ice, and the temperature will increase over that time. Then from at 0 degrees, we have this flat line for a while, and it says we have ice and water present there, because that's where we're undergoing melting. Okay, technically freezing is occurring as well, but if we're saying that the temperature is above that, or of the surroundings, that we should be changing all the ice to water. But the temperature of that substance, that ice water, will remain 0 until all of it changes into water. Then you can see that when it's only water, it will increase in temperature. And then up here, this is the part I'm ignoring. We're not doing any of these crazy triangle things. Basically, we're going to just be looking at a straight line right there. And that is where you have water and steam occur. And then where we have boiling. And then above 100 degrees, we are completely in the form of steam. So this is your standard heating curve where we can see all three states of matter when they're occurring. And when you have just the individual state, the temperature is increasing. Okay, we can increase the temperature of the individual state. But when we have a phase change, the temperature remains the same. So why is this? So let's review again. Let's talk about basically the organization of solid, liquids, and gases. So solid, all the particles are basically very fixed together, and all they can do is vibrate next to each other. Then for liquid, that's where they become a little bit more jumbled. They're not as organized, but they're still together. Okay, they're still together, but now they have the ability, I'm going to write the word flow, because obviously we know liquids flow, is those molecules can flow around each other. But they're still sticking together. They're still staying together. Okay? And then finally, in gaseous form, you have every individual molecule completely separate from each other. Okay? They are no longer bound to each other. They're no longer essentially intermolecularly bonded to each other. Okay? So what we need to kind of explain here is what's happening as I increase the temperature when it's completely solid. Well, we said temperature, again, is average kinetic energy. So what's happening is these particles start vibrating faster and faster and faster and faster and faster as I increase the temperature. Even at -2 degrees, those things are vibrating a whole lot faster than they did at -20 or -30 or wherever it is down there. All right? So we see one state of matter, they are moving, but they'll start moving faster and faster. At 0 degrees Celsius, what's happening here is I'm basically having to loosen those intermolecular forces. So all of the energy, and we talked about this, it's going into basically the potential energy of it. We're not changing the energy at all. It's just changing the potential energy of the molecules, because it's basically using that energy to loosen all of those intermolecular forces. It's not making the molecules move any faster yet, at least as an average, It's not making it move any faster, that's why the temperature doesn't change, but it loosens those intermolecular forces during that time. Then as I'm water and I increase temperature, these particles in the liquid, they continue to start moving faster and faster and faster and faster. And then when I boil, again, it goes flat because all of the energy is going into essentially breaking those intermolecular forces. I know I mentioned this in an earlier video as well when we were doing phase changes with enthalpy. Okay, so that's where the enthalpy is coming into play. So like down here where I'm talking about the ice, we'd be using the formula Q equals MC delta T. Right here we'd be doing Q equals MC delta T because we're changing the temperature. But when I'm doing the melting, I would have to do Q equals delta H fusion times the number of moles. There's no change in temperature there, so I need a formula without the change in temperature. Same thing goes with the one up at boiling. All right. Now, a couple things I do want to point out with this. I'm going to just quickly draw another one. Okay, is with the heating curve, and that's not shown on that graph so much. We should see that the boiling part should actually be longer than the melting section. And again, that is because we don't need as much energy to loosen the bonds. Remember that was 6.01 kilojoules per mole is the enthalpy of fusion, versus boiling is 40.7 kilojoules per mole. So the boiling condensation part, especially for water, is definitely much longer, and that should be true with most chemicals, if not all of them, because it's going to take more to break the intermolecular forces than just to loosen them. Another thing just to mention, we can do something called a cooling curve, and it's just the opposite. That would be where you start at the top, then it condenses, then it goes down, then it freezes, and then you go from there. So it would just be the opposite, where gas is at the top, liquids in the middle, solids at the bottom. That like never changes. It's just we're doing condensation, and then down here we would be doing freezing. And in this case, all of this time is going on, we are releasing energy. This would be negative Q's occurring there. Okay? So that is one of the graphs and kind of hitting the main points here. Again, they show the states of matter and phase changes. All the curves are essentially follow the same pattern regardless of the chemical identity. They'll just be different melting and boiling points. There are substances like carbon dioxide where the liquid section is going to be very small. All right? The difference between where the object melts and where it boils is going to be very small, which is why dried ice sublimates, okay, so quickly. Energy increases when you are in a single state of matter. It makes them move faster. That's the change in kinetic energy. Energy stays the same in the phase change. This is the energy used to break the intermolecular forces, so it's going into a change in potential energy. Cooling curves are the same, except they move high and move down. And then the main things to be able to analyze on it, identify what state of matters are present at different times. Obviously explain why the temperature is changing or not changing during phase changes, and then be able to draw the curve yourself as well. Okay? Now another type of chart we have here, this is called a phase diagram. A phase diagram. Okay? And so what we have here is again showing you a different way of what state of matter I have. But we're looking at two different things here. Well, one different thing. Mainly the idea that we have pressure versus temperature on the graph. Okay? Temperature and pressure. Because it turns out pressure does play a role in what state of matter will be present. The more pressure you have on your substance, the more you're pushing those molecules together, and therefore you could try to make it go back into liquid or even solid form if you're at a very high pressure. When there's no pressure, there's nothing having to hold those particles together like that, other than their own intermolecular forces, and in many cases they might go ahead and be like, well, forget it, we'll go ahead and all separate if there's nothing trying to force us together. So you can see the shape we kind of make with this. You can see we have our states of matter: solid, liquid, gas. Again, this is how pretty much all of the chemicals look. The only kind of difference we run into is this line over here. With liquids, it actually kind of goes in Actually, no, sorry. Liquids, it goes out a little bit more. Not liquids, water. And then most other substances, this goes in a little bit, but you don't have to worry about that too much. The main things, again, are solids are on the left, liquids are going to be between the two curves at the top there, and then gases are on the right. And I can basically say, here's a pressure and a temperature. What state of matter do I have? What state of matter do I have? And that's really what we're looking for. You can see down here at the bottom, at low pressures, we can jump straight from solid to gas, so that would be sublimation occurring. Again, the lines represent when a phase change occurs. So there's melting. Again, we could go backwards. This would be condensation, et cetera, et cetera. We can see the change that occurs. So I could be like, you have a substance at this temperature and this pressure, but then you increase the temperature to blank. What has occurred during that time? And we'd say, maybe you started over here, but then you're ending over here. What's happening? The object was solid, now it's liquid, so it melted during that time. And that's what we're playing around with. A couple points on this to point out. You can see it's labeled TP. This is known as what's called the triple point. That is a temperature and pressure where all three states of matter are actually existing in equilibrium at the same time. So that's very unique. That's very tough to do. Okay, you can see it's actually at a very low temperature. 300 Kelvin is negative 73 degrees. So I mean, it's even less than that. So that's something that's not exactly completely common for any particular substance, but it's something we could create. So triple point is when all three states of matter exist. Over here we have what's called the critical point. And usually what we see here is something like almost like a dotted line that kind of goes straight up, okay? And I know this one's showing a blue line going to the side, but this is usually like a line straight up. What that is, the critical point is basically, it's at a temperature where it's so high that only gas can now exist, regardless of the pressure. That gas exists only. Oops, sorry. Regardless of pressure. So even if I keep on trying to apply more and more pressure, the temperature is so high, the particles are moving so fast that can only be in the gaseous form. All right. So that's why we talk about that critical point. Essentially, this point, I don't want to draw it all the way down. From this point on, we're always gas. We're always vapor. Okay. So those are kind of the things that we kind of play around with it. So again, things to know: boundaries represent where the phase change occurs. Triple point, the temperature and pressure where all three states of matter exist. Critical point, temperature, it's at a temperature where the particles are moving so fast that they can only be in a gaseous state regardless of the pressure. All right? So it's just another way to kind of give you some charts to look at to understand how the phases of matter are changing, the states of matter are changing. It helps you looking at temperature and energy as well as temperature and pressure with the two different diagrams. All right? That's pretty much it. Thank you.